This video will be on graphing experimental data, the kind of data that you might gather in, say, some sort of a lab that you're doing in a science class, or maybe an actual experiment you're doing. And I'm going to point out some things about hand-drawn graphs. I'm not going to be doing these on a computer, but these will all be hand-drawn graphs. Things are a little bit different than they might be in a math class. The data that we're going to look at here is going to be for data gathered during a spring experiment, and let me show you what the experiment looks like. You'd have some sort of a horizontal support, a spring hanging from it, and then attached to that spring is a mass. The mass bounces up and down, and you time how long it takes to bounce up and down. And what you'd actually do is time about 10 bounces of it, complete cycles, and divide that result by 10 to figure out the period of oscillation. And there's a relationship for this type of motion, and it happens that the period t equals 2 pi times the square root of the mass that you have hanging from it divided by a number k, which is the spring constant. And it depends on the spring, what it's made of, what type of metal, the diameter of its wire, and things like that. Now, this is a complicated relation right here. If I was to make a graph of the period versus the mass, I'd get something like half a parabola. However, if you were to graph t squared instead, square both sides of the equation, and I'm going to regroup things here. 4 pi squared over k. Now, don't worry about the mathematical details of this. They're not what we're after. What's important here, though, is that if I make a graph of t squared versus m, it's actually a linear graph, and it has a slope given by this. So when I graph t squared versus m, I'll be able to figure out what that spring constant is, and that would be the point of an experiment like this. Now you can see the data that we might gather for an experiment like this. We have the mass coming down this column. We went from 50 grams to 500 grams, or 0.050 kilograms, up to 0.500 kilograms. We measured the period, but we're not actually going to be using the period. We'll be using the period squared. So I squared all of these numbers to generate these numbers here. And this is directions that might be given in a lab. Using the graph paper provided, make a graph of the period squared versus the mass suspended from the spring. Which one goes on which axis? Here's the way to tell. Whenever you have something that's written like a versus b, or a as a function of b, you'll sometimes see that written, the thing before the versus goes on the vertical axis. The thing after versus always goes on the horizontal axis. So that's the easy way to tell. Notice I didn't say y and x here. I just said a and b, and we're going to be talking about t squared versus m, not y and x. In science classes, you never graph y and x. You have vertical axes and you have horizontal axes. In this case, we're going to be graphing t squared versus m. Make sure your graph has all the necessary components. I'll mention what those are in a moment. You should know which quantity goes on which axis. Well, t squared goes on the vertical axis, m goes on the horizontal. Another direction here, calculate the average values of the graphed quantities, t squared and m. Plot this point on the graph and use this point to make a best fit straight line. There's a rather complicated statistical method for making a best straight line. It's called the least squares fit of a straight line. Complicated calculations, but if you do that, the best line that you draw that way goes through this average point. So we're just going to make sure this average point is on our graph, and then we'll do the best we can by eye. When you calculate the average mass for this set of data here, you get 0.275 kilograms. Just add the values up and divide by 10. When you calculate the average value of t squared, you would get 0.587 seconds squared. So there's what we have. Now let me show you the graph paper we'll be using. This is going to be a sacrificial piece of paper here. Along one axis of this I have 18 divisions. That's the long axis. And along the other axis I have 15 divisions. Okay, so 18 by 15. I'm going to consider those divisions when I look at the data that I have. When I look at the mass values, they range from 0.050 to 0.5. That's a range of about 0.5 kilograms. The 10 divisions will work well for that. I can actually double the scale so that I have 10 data points actually. I can use one major division on the thing for each one of my data points there. So that'll work pretty well. When I look at the range that I have of the t-squared values, I can only use one division for each data point here because the data is evenly spaced every 0.050 kilograms. Otherwise I would just think, well, I've got a range of 0.5, I've got 10 things, so if I let my 0.5 kilograms be spread out over 10 divisions, each tenth of a kilogram will get 2 divisions. When I look at this, it's not quite so straightforward, but I do have a range. If I subtract the smallest value from the largest value, I have a range of about 0.9, and that'll work okay if I use the 18 division part for this thing. Now this goes on the vertical axis. That means I'm going to be rotating my graph paper this way, and I'll have the t-squared on the vertical axis and the m on the horizontal axis here. Now this was a sacrificial piece of paper, but I'll write some of the things on here that have to go on a graph. One of the things that has to be here is a title, and the title should be something so that a reader can glance at it and immediately know what that graph represents. Well, we're graphing period squared versus mass. That's a nice descriptive title for this. So that's step one. Something else we have to have is each axis has to be labeled with what it represents and the units of measurement. Well, this horizontal axis along the bottom is the mass, and the units are kilograms. And I know I'm writing over some stuff here. I'm not going to actually use this piece of graph paper here. The vertical axis, what I'm going to put on it is the period squared. I use the letter capital T to stand for period, and I'm just writing it on the graph itself here. I'll move it over into the margin when I make the real one. And the units for t squared are seconds squared. So this would belong over here in the margin. Then I'll need to put the division on there, or the scale that I'm using. So the major divisions, or every other one or something, will have a number on it so I can tell what those numbers are. So I'm going to go ahead and graph the data points and put the scales on here, and you'll see the finished graph. Okay, something you can see here, I haven't graphed any data points on here yet, but I've put the scales on. The mass scale goes from 0 to 0.5 here. I could have continued it on, but there's really no need to do so, although I might put the 0.6. The largest mass I have is 0.500 kilograms, so that'll go straight up from this thing. The t-squared scale, I need to modify my graph paper a little bit so I'll have a wider margin on here, but that works anyway. But I start off down here. I don't have 0 on this axis. It's the slope that I'm after, and I don't need to have the origin on there to figure out the slope, and so I didn't bother to put it there. but then here's 0.2, 0.3, 0.4. Each major division on here is 0.05, and I go on up here to 1.0, and then I've got 1.05. Now I'll plot the data points on here and come back and you'll see the finished graph here. Now you can see the graph with all of its data points plotted onto there. The X marks the spot here in the middle is the average data point. That's the one that I'll force the line to go through. Now here's how I draw my best fit straight line when I'm not doing a fancy statistical thing. I put my pencil point in the middle of this thing, put a transparent ruler on here, and rotate the ruler until it seems to match the data pretty well. And this is a judgment call. I don't expect perfection from my students on this, but this looks pretty good right here. And so now I'm going to have to use a pencil line here. I don't want anything quite as thick as a marker on here, but you can see an approximation of our best fit straight line. So that's the process of graphing the data. The next thing that I want to do is to calculate the slope. And for calculating the slope, there's a little bit of error in reading these things. Even if you think you're reading a point that the line goes exactly through, you may not quite be right. So I picked not data points. I picked 2 points on the line that are as far apart as possible. And by picking a point where the line leaves the graph at one edge of the paper and where it leaves at the other edge of the paper, I get points that are as widely separated as possible. That way, whatever error comes from me reading the data point itself or the line point itself is minimized. So now I want to know what are the values of those 2 points, and I'll write them on here so that we can calculate the slope from that. Alright, now usually I wouldn't be writing this stuff on the graph itself, but I'm saving a little bit of paper here by doing this. I've got the mass recorded at each point. I have the t-squared recorded at each point. If I zoom in on this point, if I look at it very carefully, the strong division that's over here is 0.5000 kilograms. It's exactly that much. This one here is 0.5500 kilograms. The line is crossing just to the right of the fourth one over. That'd be 0.540 kilograms, but it's about 2/10 of the way to the next division, so it's 0.542 kilograms. And there's no reason you can't read a graph with that much precision. Record all the precision that you can and use that in calculating your slope. The t-squared is exactly 1.050 seconds squared, because that's what the top line on the graph represents. When I zoom in on this point down here, I look at that. This strong division over here is 0.1000 kilograms, exactly that. This is 0 down here, so each one of these represents 0.02 kilograms. And I look at that, where that crosses, and it seems to be about 2/10 of the way from the 0.02 to the 0.03, so I called it 0.022 kilograms and measured it that way. The t-squared value here, since it's crossing that bottom line, that's exactly the value of that bottom line, and I just wrote it here to 3 significant figures. Now for the slope calculation. The slope is going to equal the rise over the run. And that's the best way to remember the definition of the slope. The rise is how far up it goes. The run is how far over it goes. The rise will end up being the difference in my t-squared values. The run will be the difference in my m values, because that's what's graphed on the horizontal axis. By the way, notice when I recorded these 2 points, I had units with them. These data points and the line represent things that have units, and so make sure that you record the units with those. Alright, in this case, the slope will equal. The rise is the difference in t-squared values. The top one is 1.050 seconds squared. The bottom one is 0.150 seconds squared. That's the rise. The run is 0.542 kilograms, the bigger of the two values, minus the lesser of the two, minus 0.022 kilograms. I've got enough to calculate the slope here. This difference here is 0.900 seconds squared, and I want to make sure I write every significant figure I've got here, divided by 0.520 kilograms. Okay, notice I'm keeping the units all the way along the line. Also, when I subtracted here, I had 2's in the third decimal place on each. That gave me a 0 in the third, but that's a significant figure, so I want to make sure that I record that here. I know each of these numbers to 3 significant figures. That's what I can keep when I calculate the slope. The value that I get here is 1.73. The units would be seconds squared per kilogram. That's how you graph experimental data. That's how you figure the slope of it. Notice what I did with the units, with reading precision when I actually read the values here, and everything else. Okay, you'll get ample opportunity in lab to practice these skills. By the way, don't do the calculations on the graph like I did here. I just didn't want to have to be copying from one sheet of paper to another while I was showing you this. Generally in your labs you'll have a space to do these things.